Hi everyone, in this video I want to share how I use PyTorch for my master's thesis, which is titled Accelerating Molecular Docking Using Machine Learning Methods. So this work was later published and the publication link will be available in the description. And towards the end of the video, I'll also be sharing a Jupyter notebook related to the presentation, and I will also share the link to the GitHub repository for the full implementation. My name is Abdul Salam and I'm a PyTorch ambassador. Now, before we go into it, I want to talk about the Voyager program, which is really something that influenced my mindset while working on the thesis. Now, imagine NASA launched the Voyager 1 and Voyager 2 in 1977 using a technology that is weaker than our smartphones today, right? And today, for example, Voyager 1 is the farthest human-made object from Earth. And both spacecraft are still sending signals to NASA. Imagine that. So really, this is a program that influenced my mindset, which is really to focus on quality and to be very curious. So it made me work on my thesis not just for the sake of completing a degree, but to solve an existing problem and to contribute something novel in the field. Let's start going into the domain itself, which is drug design. So as we know, drug discovery is expensive, it is slow and computationally expensive. So traditional drug development can take from, let's say, 10 to 15 years, which is a long time and can cost millions of dollars. So what researchers typically do is they screen large libraries of molecules to identify compounds that bind to disease-related target proteins. And this process is typically time-consuming, as we will see. So let's start slowly going into the thesis itself. And before that, let's talk about a little bit about proteins, because it's related to that, and molecular docking. So what you see on the screen is a 3D protein ligand interaction. So the red part is a protein and the yellow part is a ligand. You can think of a ligand as a smaller molecule. And molecular docking, which is a concept I want to introduce, estimates how strongly a ligand can bind onto the target protein and for what purpose. Typically, the protein is associated with a disease and we want to find a candidate molecule that when it binds to the protein, it can inhibit its activity or can change its activity. This is the overall objective of drug design, at least for computer-aided drug discovery. So let's talk a little bit more about molecular docking. As we see on the diagram here on the right, we have a target, we have a ligand, we dock it and we get this. So molecular docking estimates how well a molecule, ligand in this case, bind to the target protein. The difficulty is that a ligand can bind to a target protein at different orientation and different positions, and typically that protein itself can have multiple binding sites, can have different pockets, and you typically have millions of molecules. So for a single molecule to dock it onto the protein, you have to try different positions, different orientations at different binding sites in some cases, and that is computationally expensive. So docking predicts binding affinity and interaction poses. Binding affinity, you can think of it as how strongly a ligand truly binds to the protein. It is the ground truth. It is what docking is trying to estimate. So this is also more like a simple diagram. We have a target protein, we have a candidate, the docking here. This is one more example. Now let's talk about virtual screening, which is an important concept. So in here, for example, we have millions of molecules. We dock them onto a target. Then we only select the ones that bind strongly to the target. So this is the basic idea of virtual screening. So what you do is you dock millions of ligands, you take them one by one, dock them, and then for that, don't forget, for each docking there could be different poses, different orientations, and different binding sites. And this process is expensive because that you might need a high performance computing. So virtual screening helps prioritize the promising ligands that could be used for subsequent experiments. So the challenge of the thesis is to really reduce the number of docking calculations. Now let's talk about sampling and conformation search. So as I said, docking explores different positions, different conformations, different binding sites, for example, in some cases. And searching algorithms are used, genetic algorithms, Monte Carlo, and molecular dynamics. I don't want to go into them. And the objective is to find low energy binding poses. Low energy generally indicates stronger and more stable binding. It might sound counterintuitive, but this is the way it is. So let's talk about scoring functions. They estimate when you have a ligand, you dock it onto the protein. The scoring function takes into account some factors to estimate the binding strength. There are different scoring functions. Some of them are empirical, knowledge-based, and force fields. There's a docking software that we use, which is Autodock Vina. It has this empirical scoring function. So you can think of empirical scoring function as a weighted checklist. It looks at factors like hydrogen bonding, distances between atoms, then combines them using weight learned from binding data to estimate how good the ligand-protein interaction is. And all this is computationally expensive. It is time-consuming, and researchers might not have access to HPC clusters. And the goal is to predict, our goal at least is to predict docking scores without actually docking every single molecule. So let's talk about our approach. What we do is, let's say we have millions of molecules. We only dock a subset of them. Out of 1 million, let's say we dock 7,000, and then we train a machine learning model to model the relationship between the docked ones and the target protein, so that for the remaining that were not docked, we were able to predict their docking scores without actually doing the docking. I used different models, Transformer, LSTM back then, and obviously PyTorch for the implementation. So for the remaining that were not docked, the trained model is used in predicting the docking scores. And this really significantly reduced the time that will be used instead for docking, while also maintaining accuracy. So let's see how it works. First, let's say we have 3.8 ligands. What we do is we select 7,000, which is 0.2%. We dock them, we get the docking scores. We train a model on those docking scores, and we get the trained model. So for the remaining 99.8 undocked molecules, we use the model for prediction, and the prediction can be done very fast. So let's talk about some important part of the project. We have a ligand, typically represented as a SMILE string. So SMILE stands for Simplified Molecular Input Line Entry System. So it is a text-based way of representing molecular structures using characters and symbols. For example, O stands for water and CCO stands for ethanol. So when we have them, they are like strings, right? We cannot train a model on strings. We need to feature them. Some of the features that we use are extended connectivity, fingerprint, and marks. Mark stands for molecular access system keys. It is like a 166, we are going to see in the Jupyter notebook, 166-bit vector. At any position, it asks, for example, does that SMILE have a hydrogen atom? If it has, it uses 1, else it uses 0. It's like, so it is essentially ones and zeros. And a descriptor that I use, of course, I embedding for transformer-based models, and I also experimented with concatenating them. Concatenation actually led to promising results. And what we understood is that this particular step significantly impacted the model's performance. So if you don't handle featureization right and properly representing the SMILEs, you will end up with a model that might not generalize well. So let's talk about the results. In terms of R squared, got up to 0.9 in a case of a particular target using actually an LSTM model. We experimented with 7,000 molecules. We also experimented with just docking 50,000 and also just docking 350,000 molecules. So in some cases, the distance, mean absolute error between the predicted docking score and the real docking score was 0.45, which is actually very, very promising. And the average MSC is 0.30. So this was really encouraging for us. It meant that there's a huge potential to speed up drug design. So let's go back to the second slide I showed you. I think it is important when working on thesis to focus on quality, to focus on the impact in the future of the work. And it is important to understand the domain. For example, this is the domain of bioinformatics, drug design. And if you are really good in the domain and you understand the different concepts, this will help you significantly to solve the problem. And it is important to be patient and be curious. Sometimes you try a solution, it might not work. You try another, it might not work. And ultimately, if you keep trying, you will end up solving an existing problem. And curiosity is also very important, I think. So thank you very much. Let's see the Jupyter notebook. Okay, so let's look at a simple example. In here, we have the spike protein of SARS-CoV-2, and we will find a ligand that can bind onto it to inhibit its activity or change it. So here, let's load the project. We have the spike protein, and this is the 3D structure I previously showed you. Let's look at the data set. In here, let's say we have 1000 candidate molecules. We're not going to dock all of them. We are just going to dock, let's say, 5 of them, and then train the model using just these 5, and then use the model to predict docking scores of the undocked ones. Let's look at the distribution of the docking scores. Okay, most between -5 and -6. And let's look at the sample smile, which is this, and this is the docking score. I'm going to use our RDKit library to look at the 2D diagram of a smile. In here, we can see the atoms and the chemical bonds in the molecule. So let's look at a particular featurizer. While you cannot feed letters to a model, right? You need to turn them into numbers. Let's use mark keys, which is 166-bit vector. At any position, for example, it asks, does this molecule have an oxygen atom? If yes, it uses 1, else it uses 0. So it is a combination of 0 and 1. Let's visualize it. So at this particular position, for example, position 57, I think, or maybe 56, it's asking a question and the answer is yes. So that's why we have yellow, which means 1. I've already trained the model. Let me load it. After loading, we have these candidate molecules, new incoming molecules, and their smiles. We don't know their docking scores. We don't want to dock them. We just want to use the model. After doing that, I just loaded them. Let's look at the 2D diagram. So we have aspirin, paracetamol, benzene, for example. So let's predict use the model to predict the docking scores. So for example, aspirin, we got this -3, and for caffeine, it is the lowest, and lowest means it has the strongest binding. Let's rank them. After ranking, caffeine is on top. Okay, this is the visualization of the ranking. So our best molecule is caffeine. This is the smile. So instead of docking it, we just use a model which can predict the docking score very fast. Okay, so this is a mini challenge for you that you can use. All right, thank you very much. Bye bye.